Ph.D. candidate, David Leon, in the home stretch of his Ph.D. And we're talking today about a recent milestone he reached in unblinding the data from Polar Bear 1. Do you call it Polar Bear 1 or just simply Polar Bear? Simply Polar Bear.
Or PB-1.
So he took 2 seasons of observation from Polar Bear, which is a telescope that's in Chile, in the Atacama Desert, at the Simon's Array site. And that was a great achievement to get to that point where you validated the data and were able to determine that it was good data and were able to unblind it so that you can now really use it. So talk a little bit about what it is that you are now able to see, or what is it, what the unblinding now allows you to do.
So the final result that we're looking at is basically a power spectrum of the gravitational lensing that we see in our data set. We know that there's a theoretical form that it should align to, and up until now we haven't looked at what that is, but once we unblind, we will actually see the result of our data and see if it matches what the theoretical power spectrum looks like.
So it was quite an involved mathematical process you went through to validate the data. Mm-hmm. Can you tell us a little bit about how you did this?
Yeah. So before looking at the final results, we want to make sure that both our data selection and our data analysis procedure are working out correctly. So I look at a number of different things. One is to sort of test whether or not there are any inherent biases or some kind of errors in our data set, and I look at a number of different what we call null tests, which are their power spectra, but they're created from the data in such that they should be consistent with zero. So I run through sets of those null tests, and if all of them are consistent with zero, then it looks like our data set is good. If some of them are not, then we know that there's either some kind of error in how we're doing our data selection or something wrong with our analysis procedure.
The Simon's Array Polar Bear, it looked at certain patches of sky, which were selected as being most representative of the CMB in the darkest places, right? Mm-hmm. So it looked to me that you compared these data sets so that they were statistically the same, which gives you the confidence that you're getting accurate data, right?
Yeah. Actually, the way we selected those patches is actually we have previous measurements from other experiments about the size of foreground contamination, and those 3 in particular are regions of very low contamination. So that went into our decision to select those patches. But yeah, you're right. We want to look at and make sure that the statistical properties of our data set is basically what we expect it to be.
So what did you find? Are you happy with the data? Is it?
Yeah. It's been a long process, but yeah, we've gone through a number of different null tests, and some of them have problems, but we've since worked through them. Those all seem to be checking out. We also there's other tests that have to do more with the data analysis pipeline itself, to make sure that if you, for example, run that same analysis on simulated CMB observations, that they get the correct results. So after going through all those tests, it looks like we're ready to look at the final result from our data.
So this data was collected around 2012, 2013, 2014, and it's a massive amount of data, right? I mean, it gave us an idea of how much of this there is. I mean, how is it collecting it? It's scanning the same part of the sky. How much data is there?
Oh, in terms of, I don't have the numbers on top of my head, but like you said, this is over basically a 2-year period, and we don't have the telescope scanning constantly because there's downtime for maintenance. There's calibration products. We look at different parts of the sky to make sure the beams are right or the gain is right. But as much as possible, we have our telescope scanning the sky constantly whenever these observational patches are observable to it. and yeah, I don't remember exact numbers of like how much space it takes up on our hard drive, but it's a lot of data.
But in terms of the data points,
Mm-hmm.
uh, Polar Bear 1 had how many pixels approximately?
On the order of 1,000.
So you've got these 1,000 pixels,
Mhm.
which give you the data for this patch continuously almost.
Yeah, that's right.
Is it 24/7 or is it limited to a certain range of hours?
Yeah, like I said, for any given point on the sky, you can only see it for part of the day,
Part of the
since
day.
The Earth is rotating. But one benefit of choosing the three patches that we did is that, as far as I know, any given point in the day, one of those three patches should be observable to us. So theoretically, we could be observing them, at least one of the patches at any given point.
But you're talking about thousands of hours of observation that's
Yeah,
been
yeah.
collecting on a continuous basis.
Yeah.
So
Exactly.
it's an incredible amount of data based upon the time that
Mhm.
it's collected and the number of data elements that you got to process.
Yeah.
So what's the next step now that you've satisfied the validity and the accuracy, the precision? Where do we go from here?
From here, I mean, basically, it's look at the result and write the paper. Really, basically, all of the analysis that has been done so far. So, yeah, next step is to write the paper and get it submitted.
And is that part of your dissertation? Is this process?
Yeah, yeah, basically, a big part of what my dissertation will ultimately be is uh, my process in analyzing this data set.
And describe to us a little bit what you're looking at gravitational lensing,
Mhm.
primordial gravitational lensing. Can you give us a little bit of a better explanation of what that is, and
Mhm.
what's the new information about that you're looking for?
Yeah. So, um, we believe that the you know the surface of last scattering is where the CMB was generated. At that point, the photons in the universe were able to essentially free stream through the universe without hitting any other charged particles like free electrons.
When it got to about 3,000 Kelvin.
Yeah, yeah. um, so in the absence of any scattering, these photons would travel in a straight line. However, that's not completely correct because we also know that as the universe aged, large scale structure forms through gravitational collapse of whatever matters out there in the universe. So especially at later times, more recent times, when we have more densely formed large scale structure, that is actually going to gravitationally lens these CMB photons, as we know from general relativity. Gravity doesn't just affect matter; it also affects light, really any form of energy. So it's a small amount, but it's detectable in our observations of the CMB that you can actually have these very old photons have their paths bent on the way to reaching us.
And what's the number that you're looking at, and as a result, that is significant?
Um,
You're constraining this number
yeah, yeah, yeah.
more than it was
Mm-hmm.
previously, and that's a big bit of progress for the cosmology
Right.
world.
Um, yeah. So the number is actually um, really it's given by the equations of general relativity. Given what we know about the CMB, uh, you can predict from adding in the equations of general relativity what this lensing spectrum should look like. So really, there's sort of a fixed form that we expect it to look like given our other parameters of the CMB. So what we're trying to constrain with this data set is to essentially show that it conforms to that. This parameter that I mentioned before, the lensing amplitude A sub L, um, the the result consistent with gravity is equal to 1. So when we look at our final result, we want to see that the parameter from our data set is consistent with 1, basically.
Well, it's congratulations on the unblinding
Mm-hmm.
and on getting this close to your final dissertation defense. We'll miss you here at the Axe Center for Experimental Cosmology, but it's a great accomplishment.
Yeah.
And thank you for giving us your time to get us up to date.
Thanks for having me.
You're welcome. That's it from today's interview with David Leon, Ph.D. candidate here at the Axe Center for Experimental Cosmology at UCSD campus in the Science and Engineering Research Facility. David is a research scientist working on polar bear at the Simons Array.